22 disasters accounting for losses in excess of $1 billion each. That's a new record.
Hurricanes, storms, and wildfires are forcing Americans to abandon their homes.
Europe's weather has gone crazy this summer.
Hi, I'm Mikhail Thompson, and I'm studying to be an architect at Washington University in St. Louis. I'm going to be your climate host for this series as we investigate climate feedback loops and their impact on the Earth's energy balance. You might be wondering why a future architect like me is concerned about climate feedback loops and the energy balance of the planet. Let me explain. Look at these two graphs. The number of billion-dollar disasters from floods, hail, wind, and storms is on the rise. Insurance rates across the country are also skyrocketing. The reasons are complex, but at the core, the problem is a climate that is changing rapidly. This rapid change in our climate is being driven by increasing amounts of energy being absorbed by the planet and trapped in our atmosphere. As the weather becomes more extreme, traditional home designs that used to be sufficient could be obsolete. For an architect like me, this means we could be on the brink of an entirely new era of design. A new era where buildings need to be designed to adapt to an atmosphere that routinely produces storms with much more energy than in the past. This means new designs for coastal regions where seas are rising and hurricanes are more intense, new designs for the Midwest where tornadoes and hail events are becoming more common, and new designs for buildings in the West that are more resistant to wildfires. A changing climate can be an exciting prospect for an architect like me. But for most people, the changes that they're experiencing firsthand can be scary. In this video series, we're going to try to get a better understanding of the driving factors behind the changes we are seeing in our daily weather and climate. In the end, it all comes down to how much energy is stored in our planet's ocean and atmosphere. In the next 3 episodes, we'll engage in several investigations to see what we can learn about how the Earth's energy balance is changing and how human-initiated feedback loops are at the root of the problem. In each episode, we'll also look for solutions that can help restore the balance of energy on the planet, solutions and adaptations that can take us safely into the future. Let me pass you on to Dr. Alden Adolph, a climate scientist from Michigan Tech University, who is an expert in analyzing how the physics of snow and ice impact our planet's energy balance.
Hi, I'm Alden Adolph. I'm a snow and climate scientist, and I study the way that energy from the sun bounces off of the Earth. When I'm not studying snow and ice, I enjoy spending time outdoors with my husband and our son, Patrick. We like hiking, skiing, running, and just enjoying the beaches around Houghton, Michigan. I'm also a huge Taylor Swift fan, and we have 2 cats named after climate scientists. In this video series, we're going to take a look at how Earth's surface energy budget is changing and what that might mean for our future climate. But we're also going to take a look at some solutions that could offer us some hope. We often hear about how carbon dioxide, a greenhouse gas, as well as methane and other gases are causing warming of the Earth. But this is only part of the story. Another important piece of the story is thinking about how the sun's energy is absorbed and reflected by the planet. Our planet is in a constant balancing act of absorbing some energy from the sun and reflecting some energy back into space. A measure of how reflective the Earth's surface is called the albedo. You probably have some experience with albedo. If you think about wearing a white or black shirt on a hot sunny day, we can understand a little bit about how albedo works. If you wear a black shirt, it has a really low albedo. That means a lot of the sun's energy is absorbed and the shirt feels quite warm because that absorbed energy heats up the t-shirt. Now, if you're wearing a white t-shirt, it has a high albedo. Even though the same amount of energy from the sun hits the t-shirt, much less of that sunlight is absorbed by the shirt. A lot of it is reflected due to the high albedo. Therefore, the shirt stays cool and you feel nice and comfortable on a hot day. Take a look at this satellite image of the North Pole in September. The sun's incoming energy interacts with the light and dark areas of the Earth, just like the white and black t-shirts. The dark, open ocean surrounding the sea ice has a low albedo, just like the black t-shirt. This means that it absorbs solar energy, which increases the temperature of the water. The areas covered by ice have a high albedo, like the white t-shirt, which means they reflect back a lot of the energy from the sun. This large area of ice, which reflects back a lot of sun's energy, helps the planet from warming too much. Albedo is measured on a scale that goes from 0 to 1. Having an albedo of 1 means that 100% of the incoming energy from the sun is bounced or reflected back out into space. Something that is pure black has an albedo of 0. This means that all of the energy from the sun that strikes that surface would be absorbed, and 0% would be reflected back into space. In our North Pole example, the dark oceans have an albedo of 0.06. This means that only 6% of the energy from the sun is reflected off of the dark oceans. 94% of that energy from the sun is absorbed into the ocean water. The ice has an albedo of 0.7, meaning that 70% of the energy coming in from the sun is reflected back out towards space. During the last 2,000 to 3,000 years, ice core records indicate that Earth's temperature has been fairly constant. These records also show that greenhouse gases in the atmosphere have been fairly constant too. This means that Earth's albedo, especially in the Arctic, is likely to also have been fairly constant. The balanced, simplified energy equation for the Earth has looked the same over the last few thousand years. The net energy absorbed is equal to the energy in minus the energy out. The energy in is the energy that comes from the sun. The energy out is what's reflected back into space. But not all of that energy actually makes it back out into space. Some of it is trapped by greenhouse gases. That means that we have to put a negative sign in our equation here because that energy trapped by greenhouse gases actually stays with the Earth. This means that if we do some rearranging, we get an equation that looks like this. The net energy absorbed by the Earth is equal to the energy coming in from the sun plus the energy trapped by greenhouse gases minus the energy reflected due to the albedo of the Earth. The net energy that's absorbed by the Earth is what ends up heating up our planet. In this video series, we want to look at the amount of energy being reflected back into space as a result of Earth's albedo. In episode 1, we're going to take a look at some changes in the sea ice around the North Pole and what effect that has on Earth's energy balance. In episode 2, we're going to take a look at some changes in the albedo on the surface of the Greenland ice sheet. In episode 3, we're going to look at some really small changes in snow and ice that can have really large impacts on Earth's albedo. So let's get our first investigation started. We're going to use 20 years of NASA images of the Arctic to calculate the ratios of the very energy reflective ice as compared to the very energy absorptive ocean. As a reminder, the equation that we'll be looking at is the net energy absorbed by the Earth equal to the energy from the sun plus the energy trapped by greenhouse gases minus the energy reflected due to albedo. So let's write this question down in your notebooks. How is the changing amount of North Pole sea ice impacting Earth's energy balance? With that written down, let's turn it over to our student investigator from this series, Amy from Grant High School in Sacramento.
Thanks, Alden. I'm Amy, and I'm a senior at Grant High School in Sacramento, California. Alden asked if I could help investigate how the changes in Arctic ice are affecting the energy balance of the planet. No problem. Here are the first two images from NASA that we will be using for our study. As you can see, the clouds have been digitally removed so that it's easier to see the ice. Sea ice in the Arctic expands in the winter and melts in the summer. The sea ice in the Arctic melts to its lowest extent in September of each year. We will look at how much area the sea ice covers between the years 1980 and 2020. To be consistent, we will always be using images from September. Let's start by making a data table with 6 columns and 7 rows. In the first column, we will write down the year each image was taken. If we're going to calculate how much Earth's energy balance is changing, we'll need a constant reference point. In 1980, there was 7.7 million square kilometers of ice. Let's add that to our data table. Each image will show the amount of reflective ice in September of that year. Let's make a column to record that. The albedo scale goes from 0 to 1, and sea ice is approximately 0.7 on that scale. This means sea ice is super reflective. 0.7 means that about 70% of the sun's energy reflects off of the sea ice. Let's include that in the column heading. In the next column, we'll calculate how much more ocean has been exposed compared to the 1980 baseline. Open ocean water has an albedo of approximately 0.06. 0.06 means that 6% of the energy from the sun is being reflected off of the ocean, and the other 94% is getting absorbed. Let's include the ocean albedo on the heading. In 1980, since it's the baseline, we would record that there are 7.7 million square kilometers of sea ice remaining. Since this is our baseline year, the amount of additional exposed ocean would be 0. If we look at the Arctic in 1985, the ice only covers 6.7 million square kilometers. If we subtract the 6.7 million square kilometers from the 7.7 baseline, it shows that in 1985, there's 1 million more square kilometers of open ocean absorbing energy from the sun. Next, I'll bring up images from the Arctic from the remaining 4 years of the study. Record the area of the sea ice, then calculate the additional amount of ocean exposed compared to our 1980 standard. I'll leave the image on the screen for about 10 seconds. Feel free to pause the video if you need any additional time. When we're done with all our measurements, Alden will come back and join us.
Thanks, Amy. Here are my calculations for how much more ocean has been exposed during our study period as a result of sea ice melting. Our challenge now is to take the amount of ice and ocean and use these changes to explore what impact they'll have on the surface energy balance of our planet. Lucky for us, the albedo, or reflectivity, of the ice and ocean can be used to calculate the relative amount of change in energy being absorbed in this region of the planet. Let's write this formula down in our notebooks, and then I'll walk through the first couple of calculations with you. What we want to calculate is the relative energy reflecting potential. In order to do this, what we need to do is multiply the area of the sea ice by the reflectivity of the sea ice, which is about 70%. Then we want to add to that the reflectivity coming from the open ocean, which reflects a lot less, only about 6%. In 1980, the reflective sea ice covered 7.7 million square kilometers and reflected 70% of the sun's energy back out into space. 1980 is our baseline year, so this means that in 1980, there's zero additional ocean area absorbing energy. If we add up the reflectivity from this area in our baseline year of 1980, what we get is an energy reflecting potential of 539. Let's add units of ERP for energy reflecting potential to our table and add this to our notebooks. Let's do one more calculation together. In 1985, the sea ice shrunk to 6.7 million square kilometers. That means that the open ocean area was now 1 million square kilometers. To do our calculation, we'll multiply the sea ice area, 6.7 million square kilometers, times its albedo, 70. Then we'll add to that the area of the ocean, 1 million square kilometers, times its albedo, 6. When I do that calculation, I get a value of 475 for the energy reflecting potential. Let's add that number to our data table. Let me pause the video here and let you finish the final 4 calculations on your own. When you're done, hit play, and Amy will be back to help you plot your data on a graph.
Welcome back. Hopefully those calculations went okay. Here are the energy reflection potentials that I calculated. I think data tell a more powerful story when shown on a graph. In your notebooks, let's put these data onto a graph that can help us understand how the energy balance of the planet is changing. Let's put the energy reflecting potential on the y-axis and the years of the study on the x-axis. You can pause the video while you plot your data. Make sure you draw a best fit line through your data that you think accurately estimates the overall trend. When you're done, hit play again and we'll compare graphs. Welcome back. Let's compare graphs. Drawing a trend line in the data was a bit of a challenge, but this is the story I see in the data. Before we turn things back over to Alden, I thought it would be helpful to add carbon dioxide data to our graph and data table. Carbon dioxide is a key greenhouse gas that has the ability to trap the sun's energy in the atmosphere. We can use the other y-axis to graph the amount of carbon dioxide. Here's a graph of the carbon dioxide from Mauna Loa in Hawaii. Estimate the amount of energy trapping carbon dioxide in the atmosphere for each year of the investigation. You can add those data to your data table and graph. Don't forget to also draw a best fit trend line through the carbon dioxide data. Pause the video while you estimate carbon dioxide levels and make your graph. When you're finished, hit play again and we'll do one more analysis before bringing Alden back. Welcome back. Since we're all estimating off the carbon dioxide graph, our numbers may be a little different, but we should be close. Here are my carbon dioxide estimates. This is what my graph looked like when I added these data and a trend line. The last thing to do before we turn this back over to Alden is to do a little analysis. We were trying to investigate how changing sea ice around the North Pole was affecting the energy balance of the planet. Now we have data that show how both the amount of energy being reflected back into space as well as the amount of energy being trapped by carbon dioxide is changing. In your notebooks, write down 2 things that you notice about the data and 1 thing you wonder. When you're finished, hit play again and Alden will be back to wrap up the episode.
Humans are changing the energy balance and temperature of the planet by adding greenhouse gases to the atmosphere. Current data indicate that the increase in greenhouse gases in the atmosphere now traps almost 50% more energy than it did in 1990. One thing I noticed from these graphs is that as we're increasing the greenhouse gases, we see a decrease in the relative energy reflecting potential. This means that the North Pole has less and less of an ability to keep our planet cool because it's reflecting less and less sunlight. What's going on here is called a feedback loop. Greenhouse gases cause the temperature of our planet to rise. As the temperature rises, sea ice melts. Melted ice exposes more dark ocean, and that dark ocean absorbs more energy, causing the temperatures to rise even more. The rising temperatures cause more ice to melt and expose even more dark ocean. As you can see in the figure, the cycle repeats, which is why we call it a feedback loop. In this video series, we're going to explore multiple different kinds of feedback loops. It's really important for scientists to understand these feedback loops because of how they can intensify climate change. While it can be a bit overwhelming to think about these spirals, there's reason to hope that we can break the cycle. This cycle gets kicked off when we introduce greenhouse gases to the atmosphere, mostly from burning fossil fuels for our energy. Luckily, scientists and engineers have done a ton of really awesome work to bring down the costs of renewable sources of energy, like solar and wind power. What's really exciting is that now these renewable sources of energy are the cheapest way to make electricity. This is where I find hope for the future. For the first time in human history, we can save more and more money while we make the switch from fossil fuels to renewable sources of energy. Saving money while reducing our greenhouse gas emissions is a major way for us to break this feedback cycle and help get the energy balance of our planet back on track. Thanks for joining us on this exploration of how feedback loops are affecting Earth's energy balance around the North Pole. The amount of sea ice that's disappearing is certainly not good. However, there's reason for hope because we now have clean energy sources that can replace carbon dioxide producing fossil fuels, save us money, and disrupt the energy trapping feedback loop. And that's really exciting to me. Come back for episode 2, where we'll take a look at how changes on the surface of the Greenland ice sheet may be affecting Earth's energy balance. We'll also look for more solutions that give us hope for restoring the balance of energy of our planet. See you there.